So today we're going to look into the proof of why the sum of the digits of any number, if that's divisible by 3, then the original number will also be divisible by 3. So this is the second part in our series. But in order to actually, we don't want to dive right into the proof yet. So in order to actually do this properly, I think it's important that we cover a few prerequisites. So there's really two things that we're going to need to understand before we can go into the proof. And that is going to be, we need to understand remainders, maybe a little bit more than we did from grade school. And then also understand something called a decimal expansion. Okay, both of these sound scary. Hopefully they won't be too scary. So let's talk about remainders. Okay, so the idea, of course, is that if I have a number, so let's say I take 23 and I divide it by 5, okay, well, we know that this is going to be 4 with a remainder of 3. You know, the way we would do this back in grade school is we'd get the division thing, and basically I'd say, well, how many times does this go in? And I'd say into 5, and I'd say, 4, and then 4 times 5 is 20, and then we would subtract, and we have 3 left over. So that remainder is 3. And that's what we want to focus on here. So there's a couple ways that we notate remainders in math. Probably the most common way is to use this mod word. So if I say, well, what is 23 mod 5? That's 3. So really what this is asking is if I take 23 and I divide it by 5, what remainder will I have? Okay, so that's one way to do it. The way that I'm going to do it in this video is going to be by using this percent sign, which is actually a very common way to do it in programming languages. And I think it'll just be a little bit more compact than using the more traditional mod notation. So just when you see 23% 5, what that really means is 23 mod 5. That's how I'd say it. And it's asking, what's the remainder when I take 23 and I divide it by 5? And I'll have 3 left over. So just to make sure that we understand this, let's do a couple examples together. So let's start with 30 mod 4. Well, if we think about this, well, what is 3 divided by 4? Well, I know if I'm looking at my 4 times table, I know that 4 times 7 is 28. And then to get to 30, I would have to add 2. So that's going to be 2. If I take 17 mod 3, we're going to take 17, we're going to divide it by 3. So look what's the next smallest number that's divisible by 3, which would be 15. So if I take 15 divided by 3, I'd get 5. And then basically we have 2 more. So this is also going to be 2. And then the last one is 24 mod 6. So if I take 24 divided by 6, well, I actually get an integer out of that one. So anytime you get an integer out of it, basically we have a remainder of 0. Okay, so keep in mind that this number over on the right side is always going to be strictly less than these numbers. So notice that 2 is less than 4, 2 is less than 3, and 0 is less than 6. And again, for the proof, it's not really important that we actually be able to master the skill of finding remainders. There's programmers that can do it for you. Just understand the concept, and that'll be the important part. So we have 2 lemmas that I want to talk about. So a lemma is just a small proof, a small theorem that'll lead us up to the main theorem here. So this is where it gets a little bit maybe hard to understand, but I'm hoping if I do an example, it won't be too bad. So for all integers, we got this crazy statement right here. It looks pretty nuts, and maybe it seems nuts, but really all it's saying here is that if I take the sum of 2 digits, and then find the remainder, modulo some d, that's the same as first taking the remainders, adding them together, and then taking the remainder again. So let's do this mod 10, because mod 10 is really easy. If I want to figure out what's 179 mod 10, well, really, you just look at the last digit. Again, this will work for any digit, or any number, or any modulo. I'm not going to worry about the proof of this, but let's just do it to make sure it makes sense. So if I have 2 numbers, 135 and 78, and I want to figure out what this is modulo 10. And there's two things I can do. I can first just add these two digits together, which we get 413, and then I'm going to figure out, well, what is the remainder when you divide by 10, which is just a fancy way of saying what is the ones digit, which is 3. But the other way we could have gone and done this is that I could have first taken the remainders mod 10 for each of these. So I'm looking at the ones digits again, so 5 and 8, adding them together. And then basically the reason why we have to do, should be a %10 here. The reason why we have to do this mod 10 again is because you might occasionally get a number that's greater than 10, so you'll have to reduce it. So notice that we get 3 again. We're just taking the ones digit here. So again, this shouldn't be too bad. The second one is just saying that it works also for multiplication. So if I multiply two numbers together like this, again, if I take the whole thing and I look at this and I say, well, what's this, the remainder when I divide by 10? That's just going to be this number, the 6 here. I can also deal with this when I first divide each of these by 10, or take the remainder mod 10. So I have 7 and 8, and I multiply those two together, which will give me 56, and then look at the ones digit there. So the key thing is that in both of these cases, regardless of the order in which you do these, you get that. And again, I encourage you to maybe look into this and try to understand what all this notation means. But more importantly, I just care about what is the general underlying idea here. Okay, so that's going to be it for this second video. Again, hopefully not too confusing, but we are going to need this in order to get to our final proof. So take care, and I'll see you in the next video.